So now let's look into some traditional machine learning methods for forecasting. Yeah, so we do global modeling across a series. We can even apply machine learning models to single time series if they are long enough. We can have longer series due to finer granularities. You can have secondly, minutely, half-hourly series available over years. We can have additional metadata. And that's where machine learning is interesting, right? So if you think about the M3 competition, that was quarterly, monthly, quarterly, yearly data, okay? And that's what ETS, ARIMA, they are designed to work on: monthly, quarterly, yearly data. So now if you have minutely data, let's say I have a year, 2 years of minutely data. So now I have a time series where that single time series is maybe 1 million data points long. So there obviously everything changes now. And then if you have covariates, additional metadata, that also favors machine learning. And the way you can do it is usually with a nonlinear autoregression, right? Yeah. And so the basic setup is this, nonlinear, non-parametric autoregressive model, where you just do windowing, and then you can use your favorite machine learning methods out of the box. We've seen in the theory in the very first session about the traditional models, we have seen that can approximate an ARMA model if we choose the input window larger than the ARMA model has it, right? So the idea is fitting MA parts is quite difficult and cumbersome. It's quite difficult, right? So the problem is the MA part. So the ARMA model, right, it has an AR part, which is the autoregression, and the MA part, the moving average. The autoregression, that's very simple. You just do your windowing, you have your time series, you do your windowing over it. That way you build this time embedded matrix, right? So you get all of these windows. And now, well, let's just train a light GBM, gradient boosted tree, or neural network, feed forward neural network, and no problem, right? But this MA part, what can we do with it? Because for the MA part, we need the errors of the windows before. So we now need to step through the series. It's like we would have to come up with very kind of non-standard fitting and so on. But it turns out, as we have seen in theory session 1, that you can approximate the MA part with an AR part of higher order. So again, we are in the same idea. Well, you need to use long MA parts to get some complexity into your model, to not have to do an MA moving average part, and then you just do autoregression, high order, nonlinear, non-parametric fitting, and with that you get quite decent machine learning models. And the other thing is also fitting MA parts is really slow, because you have to step through the whole series and you cannot just reprocess the matrix in this sense. Okay, so in that sense, quite straightforward if we do autoregression, but the problem is what to do with non-stationarity, right? So the data distribution will change over time. And now you see, this is not a problem only of forecasting, right? I would even argue many or even most real-world problems have a time series component and changing distributions. So just think about detecting cars on the streets, which is a machine learning problem, but not a time series problem. But now let's say I give you a data set from the 1970s. I mean, the cars looked very different, the streets look different. So if you train your model on that data set and now you deploy it today, it's probably not going to work very well, right? So that the distribution changes. But in time series, this is usually much more explicit. It has more impact. So in time series, that is just something that we need to always model. We cannot just kind of abstract it away Yeah. Okay, what does that mean? So I've here a nice example of a random walk time series. So that has a stochastic trend, and now I just do my windowing. I don't do any pre-processing. I just do windowing, and then I say to the random forest, right, which is the blue one here, give me a forecast. Well, I mean, because the data, like the values up here, right? Like the training set only goes up to here. Okay. So everything, so that they do kind of an okayish job to forecast it, right? Because this is now also, it is a rolling origin evaluation. So you see they are kind of just mimicking naive, which is okay. And maybe they work a bit better, maybe they work a bit worse. We don't know, but up until here. And now we have values that are higher than anything we've ever seen in our training data set, right? In the training data set, we only saw values up to, I don't know, 63. And now I suddenly tell my neural network or my random forest, here, some inputs around 80, give me a forecast. Well, they've never seen that. They cannot predict out of that. You see, like random forest, right? What does it do? I mean, it partitions the data through a tree, and then you get to the leaves, and at the leaves it just calculates an average of the data at the leaves. So if you calculate averages between, I don't know, 0 and 60, you're not ever going to get an 80, right? Okay, so that's a problem. And now, yeah, so one thing, well, here's a little math joke, right? I mean, I know you need to always be a bit careful with math jokes. Not everybody finds them funny, but anyway, I hope the audience here will appreciate it. So there's this joke that I actually got a long time ago from Rob Hindman's forecasting webpage that says dividing the world into linear and non-linear is like dividing the world into bananas and non-bananas, right? So on the one hand, linear, banana, we know exactly what that is. It's very well characterized. And then non-linear is just everything else, right? Okay, so non-bananas, everything that is not a banana. Yeah, and now I want to argue that just as there are many forms of non-linearities, there are also, well, many different forms of non-stationarity, right? So here we are in the exact same situation. Non-stationarity, we know exactly what it is. It just means that the distribution doesn't change over time, right? That I can take a window from anywhere in the series and it will have the same distribution. But now non-stationarity, that's just everything else, right? It can mean anything. It can mean a change in mean, like seasonality or trend. It can mean a change in variance, heteroscedasticity. You can get stochastic trends. You can just get a structural break where I just tell you, okay, here, up until this point here, the series was an AR3. And now from this point forward, the series is just a constant 0, right? Totally has nothing to do with what happened before. And we've seen these series, right? I mean, if you look at like tourism arrivals to Australia during COVID. Okay, well, so more tourists in summer than in winter, every year a bit more, something like that. Then COVID, oh, let's shut down the country, constant 0, right? That's a non-stationarity. Yeah. So non-stationarities come in very different ways, shapes, and forms. Here I have some examples. A typical air passenger data set, obviously, that has this growing variance, right? So this here is a lot bigger than this here, and it has kind of a non-linear trend. Yeah, I mean, in this plot, it looks maybe even a bit linear, but it's a non-linear trend. Yeah, then stochastic trends, I mean, the random walk. So basically, yeah, you have an innovation, you just make a random step, and you have nothing. And well, the coefficient is 1, so you have nothing that that makes sure that it kind of gets smaller. So that's not stationary. It has stochastic trends because you can just walk away very far from where you started. Or you could have something like this one here. There isn't really any trend. It's just multiple seasonalities, right? So that's some electricity demand. I mean, you have kind of a very strong daily pattern, and then you have these weekly patterns. So you always see here 2 days, which is a weekend. So yeah, multiple seasonalities. Okay. So how do we now achieve stationarity? Well, the classical answer is let's do differencing. So in econometrics and finance, many series are close to random walks, and their differencing is a common tool to achieve stationarity, right? So very often people would say, if the series is non-stationary, let's just difference it, then it's stationary. And that's obviously exactly what a RIMA does. So the R in a RIMA integrated, that means you do a differencing. But yeah, I really want to caution here, because differencing only solves some forms of non-stationarity and not others. And importantly, also, you lose information about the scale. Okay, you can you can bring that information later in. What some people do is they have an additional input to your machine learning model, like an additional feature, which is something like the log of the original scale, or something like that. And yeah, so differencing can help, but differencing also can help make machine learning models more robust. So that's like a good thing. Yeah. When does differencing not work? Well, I mean, we know from our first year calculus class, for example, that if you difference an exponential function, it is still an exponential function. So if you difference an exponential trend, it stays an exponential trend, right? So in this example, black line is our original data. We do a first difference, still exponential, do a second difference, still exponential. And then, well, if we do a log, then it's not exponential anymore. But yeah, but here differencing is certainly not fixing all non, like it's not certainly not making your data stationary. Yeah, as I said, differencing loses information about the scale. Well, here I have an example. So let's say we do wind power forecasting. So this is a single wind turbine. That obviously, well, and so this is a power production of a single wind turbine. So this wind turbine, well, if there's no wind, it will generate 0. And then what these turbines do is that if there's there's just a maximum of what they can produce, and then they stay there. And then if the wind blows even more, then they even switch off, right? So what we see up here is, okay, here we have just more, like a lot of wind, so it's producing at maximum. Okay, so now we difference. I mean, here obviously what differencing will do is, because here it's kind of flat, so that makes it flat down here. Here our zeros are also flat. But now obviously if you're up here, well, you cannot go higher, so you can only stay where you are or go down, right? And that's obviously what we still see down here. So you stay where you are and then you go down, right? Which what we see here. And from the 0, we can only stay where we are and then go up. But that information gets lost when we difference, right? Because everything is mapped to a 0 in the difference series. So this information that we can either only go up in the future or only go down in the future, that information is lost through the differencing.